You're the number one suspect of a kidnapping. Do you know anything about this hamster?
Where were you 6:45 last Saturday?
Because this was little Pam's bedroom.
Our forensics team sprayed luminol and discovered this at the scene of the crime.
And what we found was your shoe print on the scene of the crime.
I don't believe you. How does this luminol chemistry even work?
Breaking news, a little hamster with the name of Pam has just been kidnapped, and she was reported missing yesterday at 8 p.m. Cops initially had thought she had ran away since there's no traces of blood in her room, but after investigators used luminol to uncover the blood trail that had been cleaned up by the suspect, the cops have deemed this investigation a kidnapping. No, a hamster napping. What is luminol, you might ask? Luminol is a chemical compound known for its chemiluminescent properties, emitting a blue glow when mixed with an appropriate oxidizing agent. Its chemical formula is C8H7N3O2, and it's commonly used in forensic science to detect trace amounts of blood at crime scenes. Luminol reacts with iron and hemoglobin, causing the blood to turn fluorescent pale blue color, which can be photographed in dark environments. Luminol's use in crime scene investigations stem from research in the 1920s and 1930s, where German chemist H.O. Albert discovering its chemiluminescent properties and Walter Speck later demonstrating its effectiveness in detecting blood and traces in 1937.
So how does this reaction work? Well, luminol in its natural form is a relatively stable molecule that doesn't emit light. Think of it like a firework that's yet to be lighted. To get luminol ready for the reaction, we mix it with the basic solution like sodium hydroxide. This is like unwrapping the firework, preparing it to react by changing its structure slightly. This deprotonates luminol, forming the luminol dianion, making it more reactive. Luminol itself doesn't glow yet because it needs an oxidizing agent to start the reaction. Hydrogen peroxide acts as an oxidizer, but the reaction won't efficiently happen without a catalyst. Hydrogen peroxide acts like a matchstick, providing the energy needed for the reaction, but the matchstick won't set off a big firework by itself. The iron in hemoglobin, our blood, acts as a catalyst. The iron in blood is like a lighter fluid boosting a fire. The iron helps break down the hydrogen peroxide into water and oxygen radicals. These oxygen radicals oxidize the luminol dianion, forming an unstable, high-energy intermediate called the dicarboxylate anion. The luminol reaches a super high-energy state like a firework at the peak of its explosion, but it can't stay up there forever. The unstable intermediate quickly decomposes, releasing nitrogen gas and forming 3-monophthalate in an exciting electronic state. The excited 3-monophthalate molecule is unstable and wants to return to its ground state. As it relaxes back down, it releases energy in the form of blue light. The blue light is like the smoke that lingers after the firework explodes. But unlike the smoke, this glow only lasts for a few seconds, revealing any traces of blood.
Luminol is an essential tool for revealing bloodstains that might have been cleaned or washed away, though it is used carefully to avoid interfering with further forensic analysis. In one murder case in Washington, D.C. in 1992, luminol showed where a woman's bloodied fingerprints were dragged off on the edge of the bed before her death. Before the luminol test, there had been no visible signs of a struggle. Chloe, our resident scientist, will now explain more about the synthesis of luminol.
Let's discuss how luminol is synthesized. It was first made in 1902 by German chemist Alois J. Smith when he was studying hydroxides. The synthetic pathway for luminol that is primarily used today was published in 1934, so over 30 years later. 3-nitrophthalic acid is the starting material in this reaction, and it is reacted with hydrazine and aqueous base in the presence of a high boiling point solvent such as triethylene glycol or glycerol. The mechanism of this step involves two nucleophilic substitutions, with one of the nitrogens in hydrazine attacking the carbonyl carbon to form a tetrahedral intermediate. A few proton transfers then occur, and then the negatively charged oxygen recollapses to form the carbonyl, and a molecule of water is released. This then repeats with the other nitrogen in the hydrazine attacking the other carbonyl carbon. A few more proton transfers occur, and a molecule of water is once again released to yield the 3-nitrophthal hydrazide intermediate. In the second step of the synthesis, this intermediate is reacted with sodium dithionite, a reducing agent, to convert the nitro group to an amine group. This is a complicated mechanism, so we won't get into it, but the idea is that sodium dithionite donates a total of 6 electrons to the nitro group, which reduces it to the amine, and our luminol product is formed. Now, despite the usefulness of luminol in forensics, there are still several drawbacks. For one, it can't distinguish between human and animal blood. 2, the hemoglobin in blood is not the only thing that could activate luminol's chemiluminescence. For example, household bleach, low levels of blood in urine, and even horseradish, which contains a peroxidase enzyme, would all give false positives. Furthermore, it may dilute the blood and destroy the evidence, which makes DNA more difficult or even possible to extract. For these reasons, other methods of blood detection are also utilized, such as the Abacard Hemotrace immunological test, which uses antibodies. And it is specific to human hemoglobin only, which eliminates the possibility of false positives or the possibility that the blood found at the crime scene is animal blood, and it also perfectly preserves the DNA. However, this test must be done in a lab and is not for use by officers in the field. Now that we've learned what luminol's limitations are, we can see that it's not enough on its own to solve a crime. So let's go back to the interrogation room to see if there's any other evidence we can use to convict the kidnapper.
Where is Pam? We know you took her.
Don't want to talk? We found your fingerprint in Pam's bedroom using an anhydrine test.
And we cross-referenced that fingerprint with our database, and we found your fingerprint was a match.
But I was so careful. How did you find and uncover my fingerprint?
Anhydrine is one of the main chemicals used in formulating fingerprints. It is an organic compound that reacts with amino acids and amines to produce a purple color. There are many different chemicals used, but this one is most used for porous surfaces such as paper and cardboard. Discovered in 1910 by German-English scientist Siegfried Riemann, he accidentally created the compound while attempting to synthesize different dicarbonyl compounds. He later observed its reaction with amino acids, leading to the realization that it could be used to detect their presence due to the color change it produced. This reaction is now widely known as the anhydrine test. In our situation, anhydrine was used to obtain the fingerprints of a guilty suspect. This works because smoother and less porous surfaces have a greater chance of finding and developing these latent prints. Pros about this test is that it is versatile and can be used on many surfaces other than glass and non-hard porous materials. It can also be used on paper, cardboard, and even wood. It is very sensitive in the sense that it can even detect faint and older prints. It is easy to apply. It can be applied through a brush or a spray bottle, and it's cheaper, faster, and more straightforward than DNA analysis. Possible cons from this test is that it has a rigorous reaction condition, it's expensive when using anhydrine analogs, and in the case that steam is used to accelerate the reaction rate, it will cause background discoloration and reduce the fingerprint's clarity. Nevertheless, being able to obtain fingerprints has become very helpful. One notorious example where fingerprints solved the case is the Night Stalker. Fingerprints recovered from the hood of his car were ultimately led to the discovery of his identity. Out of 8 people with his name, his fingerprints matched the police records. He was a perfect match and was arrested in 1984. Him, along with many others, have been caught through the usefulness of this test. More on this now from our forensic scientist, Vivian.
Fingerprinting or dactyloscopy is the analysis of fingerprints for forensic and personal identification reasons. This is a reliable method since each person has their own unique fingerprint that remains the same over time. There are 3 different types of fingerprints: plastic, latent, and passive fingerprints. Plastic fingerprints are 3D impressions made into soft materials such as clay, melted wax, or putty. An example will be the bottle of beer that I made, and then I'll press my finger into it and show you guys. So then here's the ball of dough. I'll go ahead and press my finger inside of it. And then if you look closely, there are some lines from my fingerprints. Found on hard surfaces can be patent or visible or latent or invisible. Patent prints can be both positive and negative. Positive fingerprints are found and made by the fingerprint ridges being contaminated with a substance such as blood or wet paint. And then negative would be when you have your fingerprint remove some of the surface off. So again, a patent negative fingerprint is one where you're having your fingerprint remove some of the surface. For example, we're gonna have this whiteboard right here and whiteboard marker colored in on it. The surface will be the whiteboard, and then my fingerprint will remove some of the whiteboard marker. Press it in, and then you see a little bit of my fingerprint like right here.
Now I'll talk about the mechanism between the reaction of anhydrine with amino acids. So in the presence of water, anhydrine is found as a stable hydrate, and in anhydrous conditions it will assume a triketone structure called 1,2,3-indane-diide. There are many proposed mechanisms for the reaction, but the most widely accepted mechanism was proposed by Griggs et al., which produces the ammonium salt of rhumous purple or diketohydrazine diketohydrazine. The intermediate reacts with an amino acid to form an amine or Schiff base. Then, decarboxylation and hydrolysis occur. In the final step, adding another anhydrine to the intermediate amine gives an ammonium solid vermilion purple. The thing about this reaction is that it needs rigorous reaction conditions to occur at a reasonable rate. The pH must be above 4, and high humidity is required from 50 to 80% since water is a necessary reactant. Treated fingerprints must also be stored in a cool, dark environment to prevent the degradation.
You got me. Little Pam never saw me coming, and I would have gotten away with it too if it wasn't for the power of chemistry.